All right, so before we begin today, there's a few announcements. First is that the second homework is posted. So it's online now. You can download that and the data that goes along with it. That one will be due in 2 weeks from today. So I forget which day that is, but anyway, 2 weeks. A Tuesday, 2 weeks from today. And because it's due on a Tuesday, I'll have office hours that Monday before, maybe try to make them a little bit longer as well, and also the Friday before. So there'll be the normal kind of extra office hours before the assignment. So please do come that Friday so you can have some help over the weekend then. The other announcement is that the solutions for the problem set are posted on the website. And these, I actually put them under a password protection. Just when solutions are publicly available, they tend to creep into future years. And just to avoid any kind of temptations people may have in future years, I'm just going to password them. It's right there, the password's on the board, but cleverly hidden from the video camera. And if you happen to not be in class today and you're watching this over video, just email me and I will send you the password that's right over there that you can't see. I probably will hand back, well, I will hand back the graded assignments next time. Actually, I couldn't quite finish them all, grading them all, but they'll be done a week from when you turn them in. So was there anything else? Were there any other questions about the assignments or anything else? I guess there shouldn't be because there was no assignment out recently, and then you all handed it in, and you're just waiting for me to get them back. So that should be fine. I think the other thing was that the proposals are due this Thursday. If you have any questions, a lot of you have come talk to me about possible projects. That's great. If you have any questions about the suitability of your topic for this project, let me know. Just send me an email, and I'll get back to you, and we can figure out what the right scope of it is. The other thing with the proposal is that the important part of the proposal is really to get something submitted, get something in, and then we will give comment. I'll give comments about that proposal, so you can then adjust it however you want to, if there are things you should adjust, etc. All right, well, today we're going to just jump back into power systems. In particular, we're going to talk first about AC power, finishing up from what we talked about last time on AC circuits, and in particular talk about what form power takes in AC circuits and how we can use complex numbers to represent equations in AC circuits. Then we'll talk about some aspects of larger scale electric power systems. In particular, we'll talk about generators some and how generators actually work. Again, on a very simplified scale and a very, very simplified version of a generator. But given that we're talking a lot about big scale electricity and power, it's very good to know, have at least some idea about how these generators actually work and produce power. And then hopefully we'll get to it because there are some questions on the homework about this. But the last topic we'll talk about today is three-phase power. And this is how power is transmitted in the current grid. And it's good to know why we do it that way and what the advantages are of using three-phase power. And what that means also, three-phase power. Last time we were talking about, when we ended last time, we were talking about inductors. And actually we finished with inductors and got to capacitors. But just because capacitors and inductors are so tied together, I just wanted to give a quick review of this before going to capacitors, since we didn't have much time with that last time. So remember, an inductor is something that resists the flow of current. It's usually kind of a loop of wire. And this loop of wire, when the current flows through it, it creates a magnetic field that opposes the current. Now, the law of an inductor, though, really, more descriptively, is this law here. So the voltage equals the derivative of the current times the inductance. And what we saw was that when you plug in a sinusoidal voltage into that equation, into this equation for the capacitor here, sorry, for the inductor here, what you get out is that the current at time t equals this expression, where the voltage is a sine wave here. The voltage here is V max times the sine of omega t plus some phase angle. And the current ended up, when you integrate this thing, the current ended up being the same expression here. So you have a dividing factor here. You divide by the inductance times the frequency. Would be the AC frequency of the actual voltage signal. Plus you get this phase shift here, which in this case makes the current lag by 90 degrees behind the voltage. And that's what an inductor did. It scales the current by this term here, and it causes the current, a pure inductor this is, it causes the current to lag behind the voltage by 90 degrees. And as we'll see today, this kind of relationship here causes some odd things when it comes to power. Because power being the product of these two things, that seems a little bit strange, right? Because sometimes these have different signs. So what does that really mean? And we'll define that much more rigorously and talk about how this relates to the terms of real and reactive power. Before that, though, I'll just present again the counterpart of the inductor, in some sense, which is the capacitor. And the capacitor, as I said before, but just to repeat, is made a capacitor is made of two conducting plates of material. You can think of it at least like this at least. They're really close together, but they're not touching. And the idea is that charge, electric charge, will build up on these two plates. So negative charge on one side and positive charge on the other side. And the capacitor kind of stores this charge. Right? And that's what it's really doing. But more fundamentally, to our purposes, what we really care about is the law of the capacitor and sort of what the capacitor actually means in terms of the relationship of voltage and current. And here you have kind of the counterpart of the inductance equation. So the inductance, remember, was the voltage equals the derivative of the current over time. Here's this is saying the current equals the derivative of the voltage over time. So the example I gave last time was that if you were to somehow, just like a voltage source here in an inductor would be kind of a bad idea to do. This would be a DC voltage source here, and this would cause increases where the current over time would just increase linearly, because the inductor, the derivative of this is related to the voltage, so you would just get linear increase until essentially this looked like a short circuit, looked like just an open loop of wire here. The diagram for the capacitor would be that if you were to have a current source here and put a capacitor on that, so you're somehow able to maintain a fixed current over a capacitor, this would require that you actually increase the voltage linearly over time. That's that same kind of expression that we had for the capacitor here, just now talked about in terms of a fixed current source here. For a fixed current source, the derivative of the voltage will be constant, and that will make it increase linearly. This is a harder setup to get because there aren't as many current sources that we can really think about, but this is what it would do in that situation. But the more important law, as I said, is this notion of how the capacitor relates current and voltage. So, and the symbol for it in diagrams, by the way, is this, which I just drew there, is this these two bars here, which indicate kind of these plates that build up charge. Now, we can do the same thing as we did for the inductor in terms of deriving an expression for how an AC current will be affected by a AC voltage source going through an inductor. So if we have a system like this, where we have this is the symbol for an AC source. I think I said that in one of the past slides, I believe. Yeah, I used that before. So if you have an AC source through a capacitor hooked up like this, we can just use the expression of the capacitor to derive what happens to this resulting current. And here it's actually even a little bit simpler because we can just use derivatives. So all we say is that we just plug in the expression of our sinusoidal voltage. We take the derivative with respect to time, just plugging in the equation for a capacitor here, times that capacitance. And what pops out is that the current equals the capacitance times the frequency times Vmax times the cosine of this thing, which is the same as the sine where you now add pi over 2, or add 90 degrees, instead of subtract it, as we did for the inductor. What this means is that, again, the capacitor causes the voltage to change phase from, the current to change phase from the voltage. But in the capacitor, it'll actually cause the current to lead the voltage by 90 degrees. So we actually have a current here that is ahead of the voltage by 90 degrees. And this is kind of the counterpart of the inductor, right? And so as you can imagine, very informally, what you can do in practice in some sense is if you have some inductor in a system that you don't want to be there, it's causing some phase lag that you don't really want, you can actually counteract it to some degree by putting capacitors in there as well. We'll talk about how that actually works in a little bit, I think, but or maybe in a later lecture. But the basic idea is that capacitors and inductors have these opposite effects in an AC circuit. So is that clear to everyone? This notion of phase lag and the voltage and current being out of phase. Okay. Now, I talked about, I guess the big picture here is I talked about AC circuits as still somehow being linear equations. And that seems kind of odd, right? Because we have all these sinusoids that seem anything but linear, right? They're very time varying and they clearly move in nonlinear ways over time. So how are these linear? And the way we get to linearity in AC circuits is that we actually use complex numbers to represent voltage and current. And the way we do this is the following. Remember, sinusoids, any sinusoidal signal can be either a cosine or a sine signal, because a cosine is just a sine that's shifted by some amount. Any sinusoidal signal can be expressed in terms of three things, right? The magnitude of the signal. We're going to use, so this is sort of the peak magnitude of the voltage it would be, for example. Again, oftentimes voltage is expressed as the root mean squared value of that, but we'll talk about these sinusoids because it's a little bit simpler in terms of their peak value. So expressed in terms of its magnitude. The frequency, which actually we don't really care about too much because in an AC system, the ones that we care about at least, all the frequencies are going to be the same. So we're going to assume that frequencies are going to be the same. You know, we're using the grid frequency, say 60 hertz. We're just going to fix ourselves with that. So the frequency factor's in there, but we'll ignore it because they're going to be all the same over the different sinusoids. So we really just have the magnitude and the phase angle, right? How much it's shifted off from some for some reference amount. And the cool thing is we can actually express these types of quantities in terms of complex numbers. And that is really how we express at least steady state AC behavior of a system. And it's also how we get to linear equations from these seemingly non-linear effects here. So to do this, we're going to use Euler's equation. And it's really simple. It's just the fact that if we represent the voltage as the real part of a complex exponential, we can describe these sinusoids in terms of these complex functions here. So we're going to in particular say that v of t, for example, would equal the real part of v max times e to the j omega t, or in that kind of small, it might be hard to see in the video there, e to the j omega t plus the phase angle. And here we're using Euler's equation here that says that e to the j phi, this is a exponential of j is the complex number square root of -1. You might have seen that denoted I in other cases here, but the reason why electrical engineers use J is because we already have I used for current. So we're going to use J for the imaginary number. And we're going to use Euler's equation. It says that e to the j theta is just going to be equal to cosine, sorry, e to the j phi, just the cosine of phi plus j times the sine of phi. Now, one thing to notice is actually there's a little bit of a mismatch here because I'm saying that this should sort of be the, defined this before as being kind of the sine component. And here, I guess the real part by default is the cosine of this. But that can be fixed by just adding a constant phase shift to this, so it isn't really that important here. You could just as well define this as the imaginary part, for example. But we'll just define it like this and use this notation. Does that make sense to everyone, sort of that issue there? This isn't quite. This would actually mean this is equal to Vmax times the cosine of omega t plus theta. Because the cosine here is the real part of this. But you can fix that by just shifting your sort of default phase angle by 90 degrees, so it doesn't really matter. And we'll just use this expression here and ignore kind of those issues. Now, the cool part is that if we just care about steady, and this is an expression that captures that actual sinusoidal variance of over time of our expression. Sometimes this is also called, this notation here, when you include omega and t, so you include the actual time and frequency, sometimes called a Phasor expression for voltage and current. I won't use that notation too much. I'll just talk about complex numbers. But if you hear the term phasor, it essentially just means this type of representation of the voltage and current. So the property that really is nice here is that if we are just thinking about steady state behavior, that means just kind of the behavior these things exhibit over a longer period of time. We don't really care about maybe what the instantaneous voltage or current is. We just care about what it might be over some average sense. We don't, average sense is the wrong word here, but just we sort of just care about it, what it is to describe it overall, not about what it is at any particular instant in time. The nice thing there is that we can actually just ignore the particular value of time, right? Because the actual value of time is independent of the steady state behavior of these kind of circuits. So we could, for example, just represent the voltage as being e to the j times phi, where phi is the phase angle. This will be a complex number, but what it encodes is really this type of sinusoid. But we're doing it in a way where this is just a single number again. We don't have to worry about the actual value of time. We just have a real part and an imaginary part for representing voltage. And we'll do the same for current here. We'll represent current as these imaginary numbers, where intuitively what we're really doing there is we're thinking about this in terms of these complex exponentials. And as you work with these a little bit more, these hopefully make a little bit more sense. And we'll talk about kind of the phase angles of these things, what those terms actually mean. But the basic idea here is that we can represent AC voltage and current using, rather than sinusoids, we just use a single complex number to represent AC voltage and current. Does that make sense to everyone? Have people actually raise their, by a show of hands here, who has seen sort of this, who has seen this before? Okay, so maybe, hopefully it makes sense to everyone. Now, just as we did for deriving expressions for the voltage and current, for the voltage and current under capacitance and inductance with this explicit sinusoidal representation, you can follow the same logic and get these quantities for how voltage and current are related when you have an inductor and a capacitor. And they're fairly simple, so I won't really worry too much about those. To derive those, we do have to go back to our form here that has the full exponentials and includes time, because the inductor and capacitor took derivatives with respect to time. But the basic idea is, for example, for the capacitor, we have the current equals C times the derivative over the voltage over time. So let's plug in kind of our complex exponential formula for, not partial derivative there. We'll plug in our complex exponential formula for the voltage here. So that would be V max times sine, or rather, sorry, V max times e to the j omega t plus phi. We differentiate that. What falls out, what the terms that multiply t here that would fall out would be I equals c, a j and an omega, times the capacitance there, times V max times the derivative of the exponential is just that same thing again, j omega t plus phi. Right, and now we divide both sides by this term. When you divide by j, you have to negate that, and j remains on top there when you're dividing by the imaginary number. So this just means that, and then this term is the same as the old voltage as it was before. So this just means that V equals negative j 1 over c omega times I. Is that right? Yeah. So if you want to try to derive the same thing for the inductor, it's the same type of manipulations there. Does everyone see that? The only real trick here is when you divide by j, you don't have it on the bottom, you have it on the top of the fraction still, but you have to negate it. That's just the rule for dividing by the complex imaginary number. So I guess as we're talking about how to manipulate complex expressions, it's good to just talk about some basic rules about how you manipulate such expressions. So a couple things that will be important that we'll use again and again in the class. One is this notion of a complex conjugate. So suppose that, I guess I don't have to write all these out, but suppose that x equals a plus b plus jb, and y equals c plus jd. So we just have two complex numbers here. A few terms that are, and remember, a complex number you can represent in terms of its real part and its imaginary part. That represents all the possible complex numbers can be represented in that form. So an important notion is just the complex conjugate of a number, which is just the real part as before, but then you negate the imaginary part. Turns out that will come up all the time when we're manipulating expressions with complex numbers, and so we'll use that conjugate a whole lot. When you have a matrix of complex numbers, sometimes that little conjugate sign means you transpose the matrix and take the conjugate, and sometimes it means you just take the conjugate element by element. I'll try to specify which one I'm talking about in most cases there, because it can get a little bit confusing. So adding things is easy. Adding two complex numbers is easy. You just add their real parts, a plus c, and then you add their imaginary parts, b plus d. Multiplying them is actually also pretty easy. You just write them out. So a plus jb times, wrong things here, plus c plus jd. You just write out each term together. So you get an ac term. You get a j times bc term. You get a j times ca term, plus da term, da. And then you also get a j times another j here. Now j times j is the square root of -1, so j times j is just going to be -1. So you subtract here b, d. And this is real part here. And then you can also write similar expressions for dividing by taking the inverse of a complex number. It's a little bit trickier here what's actually going on. This is actually much easier to express in a different form, which we'll get to in a second. But essentially, this is the actual rule for what the inverse of a complex number is. And to divide one complex number by another, you just multiply by the inverse. So you have expression for the inverse, expression for products here, and you can use these to actually do multiplication. Now, it's a little bit cumbersome for the division there. Another really nice way of expressing complex numbers, which we'll use a lot in this class, which is really nice for power because it kind of captures, in power or in voltage and current, this complex portion in some respects captures that phase angle, right? What we talked about before was that, well, I guess I didn't write it here, but when you just have, without this omega t term here, the complex portion here captures kind of the phase angle of the term, and the real portion captures the sort of zero phase angle portion. And so because of that, there's a sort of a natural congruence between what's called the polar form of a complex number and kind of physically what's happening with the voltage and current there. So we're going to use polar form to describe a lot of these complex numbers. And the basic idea here is that, and again, this is high school math, so I'm sure this is a review for most people, hopefully, but I hadn't seen it in a whole lot of time when I started working in power, so it's maybe good to just remember a little bit. So you can represent complex numbers by looking at the imaginary and real, the imaginary real plane here. So this axis corresponds to the imaginary plane. This corresponds to the real axis and the imaginary axis. It's a bad way of labeling it. I'll just label it like real, imaginary. And so any point can here be described as having a real component and an imaginary component, where this here would be A, the real component, and this would be B, the imaginary component. You can also describe a vector like this, though, in terms of its length or radius and its angle from the origin. This is called polar form for complex numbers. And it can be oftentimes a lot more useful and kind of handy to express complex numbers in this form. Part of the nice thing about this form is that we actually have an easy way of doing multiplication and division, which correspond very nicely to their polar form. So addition is actually harder. Now, of course, you can convert between these two things. Basically, if you just write this expression, a plus jb equals rj to the theta. And by the way, r ej to the theta, r here would be the radius, and j of theta would be the angle that you have, right? So we also write that as r angle theta, just for convenience. And you can obviously convert between these two forms pretty easily, right? You just take, essentially, the r would just be the square root of that thing, and theta would just be kind of an inverse tan function or something like that. The nice thing about the polar form is it's very easy to multiply and divide numbers in polar form, complex numbers in polar form. So it was kind of a little bit cumbersome up here. It's a lot easier there. When you have 2 r1 theta 1 times r2 theta 2, that just equals, all you do is you multiply their radiuses or magnitudes, r1, r2. I guess that should be r1 here. Sorry, it should be r2 and theta 2 there. That's a typo. And also below here, this should be r2 and theta 2. But it's right over here. So you multiply their magnitudes, and you add the two angles. And for division, and it's pretty easy to show these properties hold just from some algebra here, but I won't do that. And for division, you just say that r1 over r2, theta 1, theta 2, you just divide the magnitudes and you subtract the second angle from the first. So that's a bit more or less cumbersome. So that is less cumbersome than this sort of nasty expression here for division. Of course, if you want to do addition, actually, now it's sort of nastier in polar form. So each one has advantages. But oftentimes, we will actually want to use polar form to describe complex numbers for AC systems, again, because this sort of notion of the polar form captures very nicely the, given that R theta equals R E J theta, this captures very nicely the kind of expression here and the actual phase angles of the voltage and current waveforms. Okay, so that hopefully gels with everyone, or at least refreshes your memory about these things. Now, the cool thing is that when you express, I alluded to this before, but when you express voltages and currents in terms of these complex numbers, you get back to linear equations. So remember, we had this expression of Ohm's law for resistances, and this is just for DC circuits, though it also applies to AC circuits. We had this expression that the voltage equals the resistance times the current. I'll write it like this. Yeah, I'll write it like that. Resistance times the current. And this was sort of nice because it linearly related these two things, and this resulted in what we call linear circuits, where you can solve for missing entries in the voltages of the currents using a linear set of equations, right? You basically do some matrix inverses to find one from the other here. Or if they're scalars, you just do a division. Now, remember that what we derived for these complex forms was very similar looking expressions for voltage and current here. For capacitance and inductance, how they relate voltage and current. And these are also just linearly relate voltage and current using some complex number. The only difference is it's a complex number now instead of just a real number. So in fact, for AC circuits, we can generalize this to say that V equals Z times I, where Z here is called the impedance. Impedance captures both resistance and conductance and capacitance here in this sort of one catch-all form here, where Z equals just the combination of kind of all the rules we know. So for Ohm's law, you just have the R there. For the capacitor and the inductor, you had these expressions here, so we just add them together. And that gives us our expression for what Z is, what this impedance is. So impedance times omega, inductance minus 1 over omega times the capacitance. Sorry, I said conductance there. I think I meant capacitance, clearly. Sometimes you'll also see various portions of this. So just the imaginary portion here is also called reactance. So impedance breaks down into reactance and resistance. They also all have terms for the inverses too, which I can't even remember sometimes. The inverse of impedance is something, and the inverse of reactance is something. One's called like susceptance, but I forget actually which of those two is right. But don't worry about those. All we'll really care about here is impedance, which is this combination of the laws of Ohm's law, essentially, for the resistance, for inductance, and for capacitance. And, as I said before, this generalizes to more than just the single variable case, but it actually also serves just as well in the matrix case. So if you have these big networks where you have many voltages and many currents, you can describe, just as we did for DC circuits, you can describe AC circuits in terms of a big matrix of impedances. Sorry, the inverse of the impedance is called the admittance. And that's from that one we actually will use. So susceptance, I think, is the inverse of reactance. Does anyone know if I'm right there? Yeah, there's no point in remembering all these names. They're sort of silly. But you will actually see this. The inverse of the impedance matrix is called the admittance matrix. And we'll use actually both those two things. Because if you have And the other side, multiplying voltage, you want to have kind of an inverse of this, which is what we call the admittance. So again, this is the Ohm's law for the case of AC circuits, and it generalizes to the case where V is now, and it's not a real number anymore, it's actually a complex number in R. I just say Rn by default almost when I'm talking about vectors, but it's Cn, and I is a vector in Cn. Here Z then would be a big complex n by n matrix. And you can generalize this expression to that case of many values. And in fact, for impedances, we have much the same rules as we did for resistances. Namely, you can take any kind of impedance elements you want. You can take an inductor, a resistor, and a capacitor, put them in series, and their impedances will add. If you put them in parallel, their inverses add. And so to get the impedance of this whole thing, you take the inverse of the sum of the inverses. So both these laws that we had, these sort of simple laws for combining resistances, they extend immediately to the case of impedances. So we can use much the same kind of expressions as we did for resistances to solve circuits that have complex numbers as well. Now, of course, just as we did for DC circuits, it's kind of a pain to do this a lot of the time, right? So if you have a circuit like this, again, you can write down linear equations for this circuit using Kirchhoff's voltage law and Kirchhoff's current law. But it's a total pain to do that in a lot of cases. This is not too bad, but when you start getting really complex networks, it gets less fun to do this. And you probably have done this in classes a while ago, and never want to do it again. So the cool thing here is that, as we did before, we can use simulation software to compute AC solutions to circuits, much in the same way we did for DC circuits. So on the homework, again, you'll do this. You'll use the same Quux software. So I'm going to draw this really quickly here. It shouldn't take too long. But just to capture the point that basically all the stuff that we did for DC circuits in that drawing program will apply to AC circuits as well. So let me just launch this guy here. Oops, somehow there he goes. OK, so let me draw this little circuit here. And I'm doing this really just because when you use AC components, there are a few. Can everyone see this OK? Is there something that happened? OK, yeah. So when you use AC components here, there are a few more hoops to jump through. You have to set up an AC simulator instead of a DC simulation. And you have to make sure that your frequencies are right and all this kind of stuff. But it's pretty simple here, too. So in our sources dropdown, just like we before had DC voltage sources, now we can drop an AC voltage source here. And it doesn't show it. We'll make it, actually, I'll just make this actual drawing here. So we had 5 volts here. So we'll make it 5 volts. But one thing to be careful of is that you actually have to set the frequency too. So this frequency by default is set to 1 gigahertz, basically for simulating really fast, sort of smaller scale, very, very fast type of electronics. And so we'll instead make it 60 hertz, which is what kind of stuff we're going to be dealing with in power systems. You can also set the phase angle here, the initial phase angle. And don't worry about theta. Theta is something. Theta, I believe, is the damping. Yeah, we won't worry about that. That's only for transient simulations here. So you can set the phase angle too, and we'll set it at 0. So we specify the reference voltage as being a 0 phase angle. OK, now let's drop in all our little components. And just like as we did before with resistors, we have a bunch for capacitors and inductors here too. So let me figure out exactly what this little thing looked like. So I had 2 inductors there. Boy, see if I can remember where all these went. Maybe you can remind me where these things went. So there was an inductor here. There was a resistor. It was here. Left? OK. I already got it wrong. Left, and it was here and the bottom, right? And we had capacitors here and here. Let's look at what the actual values are. Remember, inductance is measured in henries, capacitance is measured in farads. In some sense, though, the units here, when you think about these units, you have to also multiply by the frequency. So if you sort of want to think about them on the same scale as resistances, you have to multiply that by that frequency, because remember, our laws for our extension of Ohm's law here had the frequency multiplying the inductance and the capacitance here. Again, and that's frequency in radians per second also. But again, they aren't really comparable, obviously, resistors and capacitors and inductors, but just keep that sort of general sort of scale in mind. OK, so let's wire this all up, see how fast I can get at this. It's hard to use a trackpad to do this. I could do it a lot faster otherwise, but. OK, getting there. And we'll connect it to the other side, and we'll add a ground also. You don't have to add grounds, but it's good to, in general, have a reference voltage. Quux kind of just complain sometimes if you don't have a ground reference. So, oh, and look at set the actual values of these things. So what did I have for all of them? I had, so the resistors were all 1 ohm, and the capacitors and inductors were all 1 millifarad or millihenry. So 1 millihenry, 1 millihenry, 1 ohm, 1 ohm, 1 ohm, and 1 millifarad. OK. And now what we do is we drop this simulation block. And here we're going to drop an AC simulation block instead of a DC one. So that drops our AC system. Now, the AC simulator in Quux by default is actually meant to sweep over a range of different frequencies. And you don't want that here. You actually just want to simulate one single frequency. So we'll edit this, and we'll say that the start and stop are both equal, and they're both equal to 60 hertz here. And you have to do this. You have to set both the, actually, sorry, we want to change the type from, this would be a linear sort of interpolation between different frequencies. You want to set this type instead to just a constant. And then you just pick one value of the frequency. You have to do this for both the power source and the simulation block, actually, I think, in practice. It's sort of weird you have to set both those things, but I believe you do have to set them, so be careful for that. Make sure to set your voltage sources at the right frequency and your simulation block at the right frequency, or you will get very weird kind of results. OK, so now I run. I think I have to save it first. So circuit 4. And everything looks good, no warnings or anything. And so now let's analyze what the different resulting currents may be. So I think we wanted to look at the current, what it would be up there. So as before, we're going to do this nice little thing where you just, instead of having to build this silly thing or write down all the equations, you just drop a current probe into the circuit. And you have to simulate it again, actually, to make it get that current probe. And then in our diagrams, we will plot some values here. And we're going to plot the value of this probe, the current picked up by that probe. OK. And I guess, right, OK, so where's the, yeah. So by default, then, this says that our current is 1.7 amps at 33.5 degree phase angle. So this by default, we'll write it in polar form. And so our current is given in terms of the magnitude. And that's determined by all these elements here, as well as the elements also determine the actual phase angle. Let me see if I can figure out how to do, whoops, what happened here? I've somehow crashed this thing. I've lost my ability to select anything. Well, that's a shame. You can do this, but you can also change this to, it's not letting me do it now. I would, if I could select these things, I could do it better. Shoot, I forget how to do this now. But you can also set this to, rather than displaying in polar form, you can also display these things in real and imaginary form. We'll typically display it in polar form by default. It typically ends up being the more intuitive way of describing phases, but if I'll send out an email when I figure this out. You can also do all these things. This document settings. No, OK, I won't worry about it right now. But you can also display these things if you want to in real imaginary form. You can also, of course, just convert that yourself in your head, but or on paper. But you could also get Quux to report those values. So again, some people were asking about how Quux actually does this. And the nice thing about a lot of these networks is it's actually very easy to make kind of general rules about how you construct these matrices here. They oftentimes aren't the most intuitive ways of constructing them. So if you were to solve it yourself, you'd want to solve it in a little bit of a reduced form from that. But there are very kind of formulaic ways to automatically construct these types of reactance or admittance matrices. And that lets us essentially oftentimes just be able to build a simulator like this that can easily solve things like this, even though that seems hard to solve ourselves. We don't have to go through that kind of. I remember it being very hard and taking a lot of intelligence to do this, and so it's sort of sad that actually a computer could just do it in a very automated fashion very, very quickly. Because it seemed like something that required some amount of intelligence to pick all which nodes you were going to use and that kind of stuff. But no, it can all be automated, and it's all actually very easy to do. So I guess that's good and bad. OK, so that's how you go about solving these things for the purposes of our class, at least. If people want to solve any of these on your own by writing down these equations with Kirchhoff's voltage laws, you can, but I wouldn't necessarily encourage that. I will describe how you form actually the inverse of, or an inverse of this matrix, because their matrix is actually singular in some cases, so it has no actual inverse. But I will talk about how you form sort of the counterpart, which is the admittance matrix in similar situations. And that was what sort of is, in the case of power networks with sort of simple mesh networks, you can actually come up with a pretty formulaic way for constructing these things. And we'll talk about that a little bit when we get to power systems. All right, are there any questions here? OK, great. So now the last bit today, which actually was the first thing I wrote on the outline today. So unfortunately, probably won't get to three-phase power today, but we will certainly next time. We're going to talk about AC power now. Now, when you talk about power in the instantaneous sense, so power kind of right this second, or this instant, there's still the equation we had before, right? So power before, change colors. Let me go back to black. Power before was just the product of voltage and current, right? Power equals the product of the current times the voltage. And that still holds true in the instantaneous sense. So in the AC sense, and you never really use this kind of power in AC systems because it's almost inconsequential for reasons we'll see in a second. But the power kind of at this instant is just equal to the voltage at this instant times the current at this instant. I don't know why I flipped the order there. It doesn't really matter. They're just scalar equations. So this is the general expression for what power is in that instant. And if the power and voltage are in phase, so if we have a sine wave where the voltage is doing this, and maybe the current is doing the same thing, that's trying to be the same thing there. It's not doing some weird thing there. It's just doing this. Then this product is always positive, right? Because when they're both, it's a really bad drawing there, but when they're both, when they're in phase, they're either always both positive, both voltage and current, or always both negative. And so power will always be positive. And in fact, you can use some rules from trigonometry to show that actually this product is another sine wave with twice that frequency. So it actually ends up being something like where you go through a whole cycle. It actually ends up being a cosine here. So it goes through like this, which is actually a sinusoidal waveform as well, but just with twice the frequency. So the important part, though, is when this is always in phase, when current and voltage are in phase, this is always going to be positive. Now, remember, what we said about capacitors and inductors is that they actually made power and voltage go out of phase, right? So you can have a situation, too, where power and voltage aren't always both positive or both negative. And in fact, when power and voltage are 90 degrees out of, current and voltage are 90 degrees out of phase, this power, instantaneous power term, will be positive and negative for equal times. So it actually will be like a sinusoid that is sometimes positive and sometimes negative. This is kind of strange, right? Power is sometimes being used. When it's positive, you're kind of using power. And when it's negative, you're actually kind of generating power, right? Oh, by the way, if these are 100%, if these are completely out of phase, that would be like a generator, right? That would be, always, power will be always negative. So you're essentially, I guess depending on what you think of as the source or the sink, if they're completely out of phase, 180 degrees, then it would always be negative. But when they're 90 degrees out of phase, you have the situation where it's sometimes positive and sometimes negative. And so you're kind of, as I said, generating power some of the time and taking it out other times. And this is what's known, this phenomenon here leads to what we call real and reactive power for a system. So AC power really does not have just one component, it has two components. It has real power, and real power you can think of as like the constant term here of this sine wave. So real power is the portion of power that you actually are taking out, the positive portion that you're taking out through one of these cycles. Whereas reactive power is that portion of power that you kind of take out and then regenerate every single cycle. Actually twice a cycle. So if you've heard those two terms before, that is the definition, or that is sort of the intuition behind real and reactive power. Power instantaneously can be negative, and so there is this notion of a component that is kind of coming in and out. Now, this case here, in this case, all this power we are showing, so if current and voltage are 90 degrees out of phase, then we are in fact generating and consuming the same amount of power every cycle. So this is only reactive power. There is no real power here, because all that power we are consuming, we are generating back in the cycle. Similarly, this situation would be all real power and no reactive power, because we are only, power here is only positive, so we're only taking out power. If you have a situation where the current lags or leads the voltage by less than 90 degrees, so you're kind of in between here, being in phase and being 90 degrees out of phase, you will have some component of both real and reactive power. But these situations here are either the pure real power case or the pure reactive power case. Again, show of hands, who here has seen real and reactive power before? Okay. So does this make sense? Because it is really kind of weird, the idea of reactive power, especially when we talk about reactive power being consumed by things, because that isn't really consumed, right? But we'll talk about it kind of being consumed. What that means is there's something like an inductor in the circuit that is actually causing us to have reactive power. And we'll talk about a little bit in a second why that might be a bad thing. There's a question, though.
So this one shows pure reactive power?
Yes.
What if they are all negative?
So right. So if you have a situation where the current is completely I didn't. What did I want to draw here? So if the this is the voltage, and the current is completely out of phase with the voltage, then the product would always be negative, right? So you have something like this. And this is actually also all real power. It's just negative real power. The power is always being, in this case, generated, I guess, in some sense you can think of it. But there's no component that's kind of being generated and put back every time. What's really confusing is that the convention we have on reactive power is if the current is lagging behind the voltage, there will be some reactive power, right? Because we'll be sort of taking stuff out and putting it back every time. And by convention, if the current's lagging the voltage, we call that positive reactive power. If the current was leading the voltage, so we actually have a capacitor, for example, in here that causes the current to lead the voltage, that would still be purely reactive power in some sense, right? Because we'd still be taking it out and putting it back in every time. But by convention, we call that positive or negative reactive power. So positive reactive power is created by an inductor, and negative reactive power is created by a capacitor. So, or in other words, inductors sort of consume reactive power in some sense, and capacitors create reactive power. Which are really weird terms, right? Because there's really nothing being generated or consumed, really. It all is being generated and consumed once a second, but it's common to think of it in this way because when you have big generators operating in a power system, for example, if you do have an inductor in a line, in some sense you still have to provide that amount of reactive power, whatever that really means. But we'll talk about that more when we talk about generators. So this is one of sort of one of the initial kind of tricky things to think about when we talk about AC power, is that it isn't one thing anymore. It's these two different components. Now, this can be simplified a lot by actually, as we did for voltage and current, talking about power in terms of complex numbers. So the expression for complex power is if we treat voltage and current themselves as complex numbers. Remember, that was our convention. We wanted to treat them as complex numbers where the magnitude was the magnitude of the sign, and then the polar part was the phase angle for the voltage or current. Then the expression for power, and complex power is usually, rather than writing it as P, we write it as S. Complex power equals 1/2 the current conjugate times the voltage. And for our purposes, we'll just take that as a law. The way you can derive this is actually look at the phasor representation where you have those omegas and t's, and you'll see that actually something like this will give you those double waveforms that actually sort of describe what the voltage is. But really, we'll just think about it in terms of this being kind of the law here for what complex power is defined as. We have a 1/2 term here, and that comes from the fact that we're actually thinking about, so the notation I've used so far is we talk about current as a complex number as being or say voltage. Say voltage equals the maximum voltage times e to the j phi here. If we were to use the convention of describing voltages in terms of their root mean squared magnitude rather than their peak magnitude, this 1/2 would drop out. But since we're using kind of implicitly, we're using peak magnitudes here to describe the voltages, we actually will have this 1/2 term here in complex power. And we can write this as either in polar form or in rectangular form here. And in rectangular form, when you explicitly represent the real and imaginary parts, typically write it like P plus JQ, where P here now exactly corresponds to the real power, and Q corresponds to the reactive power. Sorry, the real power and the reactive power. P is real power and Q is reactive power. So this lets us actually determine from any two current and voltage waveforms exactly what the real power is and exactly what the reactive power is. We can also write this in terms of, I'll just use bars around S here to sort of say the magnitude of S times some angle theta. And in this notation, the absolute value of S here is known as apparent power, and theta here is called the power angle. This is a lot of notation, right? You have three different things in some sense. You have P, which is the real power. That is the power that is actually being consumed in total over one cycle. You have Q, which is the reactive power. That is the power that's being consumed and generated through one cycle equally. In general, when, again, you can sort of verify this, but if these two things have the same, this would be actually a good thing to check. If these two things have the same angle, then the complex number, and actually we can just do that. So suppose I and V here had the same phase angle. Then S equals 1/2. Remember, the conjugate of I, you just negate the imaginary part. So that would be, we'll say I max e to the negative j phi. V here would be V max times e to the j phi. When you multiply exponents, you add their powers. And so these would cancel out, and you would just have this equals 1/2 I max V max. So clearly there is no imaginary portion there. And so this would be entirely real power. You can check, too, and this would be a good thing to check, actually, that if these are 9 degrees out of phase, what do you get there? You'll end up still canceling these things, but what you'll have left, actually, I'll just do it here. So if these are 9 degrees out of phase, and say this is pi over 2, right, you would have this times that plus e the pi over 2, e to the j pi over 2, and that is just the purely imaginary number, right? That's the sort of, this phase angle is rotated 90 degrees, and so that's a purely imaginary number. So this is all imaginary then, and all you have is real power. Sorry, all you have is reactive power there. Yeah?
Can you explain again why you take the conjugate of I?
So, yeah, so we won't worry about that too much. We'll just take it as the rule for how you do power. One way you can think about doing that actually is if you think about actually multiplying the sinusoidal terms. When you multiply two sinusoids, as you saw in the other thing, you actually get a sinusoid with twice their frequency. So if you were just to multiply them together, you wouldn't get what you wanted here. You actually would not cancel these things here, and you'd get a sinusoid with twice the frequency in there instead, which is actually not what you want. I mean, that in some sense that represents kind of the instantaneous power, but it's not. It doesn't sort of cancel the phase angles. This, taking the conjugate here, lets the phase angles cancel, and you look at just their kind of steady state real and imaginary portions.
Okay.
That's sort of the hand wavy description, but that we'll sort of just take this as a definition of what complex power is here. I mean, you can try it, right? If you didn't negate these things, you'd have 2 j theta here. So you'd have a 2 j theta, so you would actually be, in some sense, increasing. And if you write that with the actual omega and t terms, you actually would be doubling the frequency. That kind of is giving you the actual sine wave here of power. But you don't want that here. You actually don't want the sine term. You want just without, you actually rather, when you represent things as sort of steady state values, you want to get rid of that t omega t term. So the way you get that omega t term to cancel is you actually just negate one of these two phase angles. And that corresponds to the conjugate there. Does that kind of make sense?
Yes.
Okay.
I mean, it makes sense like why it works out that way. I just, I just don't have a good intuition of what negating the phase would be.
I mean, it really is just meant to make them cancel, so that you look at, so you're looking at the steady state values. That's really all it is, I think. You can view it that way.
Okay.
Okay, so that's real and reactive power. Let's see what time we have left. Hopefully we'll get through power today. Yeah, we should. Apparent power, as I said, is just the magnitude of this complex power. And by simple kind of complex arithmetic here, we have that the magnitude of S is just equal to the square root of the real power squared plus the reactive power squared. So apparent power is just kind of a square, it is just the square root of the sum of both these things. Finally, another common thing you'll see is that, again, using kind of the basic trigonometry from complex expressions, the real power is equal to just the apparent power times the cosine of the power angle. So if you have completely real power, this term, the power angle, will be 0. So this is just going to be equal to, the real power will be equal to the apparent power, because there's only real power. And similarly, the reactive power is just equal to the apparent power times the sine of the power angle. And the last bit of notation you'll need to know, I think, for this is something called power factor. And power factor is just equal to the ratio of real power to apparent power, which also just equals the cosine of the power angle. So power factor is just how much of the apparent power is due to real power. And power factor is very important in a lot of cases. We'll probably talk about this a little bit more later in the course, or in the next lecture even. But one way to think about why reactive power might be kind of a bad thing is that if you have a lot of reactive power, you aren't really accomplishing anything from it, right? You're just generating it and putting it back in every single time, every single power cycle, right? So you couldn't really be doing any actual work with it, or you'd be somehow taking power out. You'd be essentially violating conservation of energy if you were actually doing any work with reactive power. Sorry, did I say apparent power? I meant reactive power. Reactive power is a bad thing because you can't really be doing any work with it. So if you have a lot of reactive power in a building, for example, that's power that's just kind of going back and forth all this time through the circuits here. It's creating current still. I mean, in order for reactive power, still causes a current to flow, certainly. And when you have current flowing, you have things like losses from current. And that happens at the grid level too, right? If there's reactive power flowing through the grid, those are power kind of going out and coming back, or being consumed and generated every single AC cycle, creating a current through transmission lines, but not really doing any work. Now it turns out that utilities can only really bill real power. That's what they sort of monitor. I mean, they could bill other things, but what they do bill is real power. They bill for the ability to really kind of do work in a system. So when your home is being billed for power, that is the real power you're being billed for. But reactive power is kind of bad from their perspective, right? Because it's causing these line losses, it's causing them to need to have more capacity in the lines, maybe, because they need to be able to handle this extra current. So they don't like reactive power, a lot of reactive power. And because of this, what they often will measure is the actual power factor of, say, a load, a big building. They will measure its power factor. And there are actually some regulations about big buildings cannot have their power factor below a certain number. So you try to have power factor above, like, I think it's 0.9 is a good sort of aim for it, even though a lot of things actually do have big inductive loads, and so they actually can easily cause it to have power factor less than 9. In that case, they're actually, what you would want to do oftentimes is do things like add a bunch of capacitors to your load to actually, that would shift, that would make the current lead more compared to the voltage, and that would decrease your consumption, quote unquote, of reactive power. Those things will hopefully all become more intuitive to you as you work with this a little bit, but that's the basic idea, is that reactive power is bad from a utility's perspective, and so to counteract this, oftentimes actually there are devices you can buy that will try to shift your power factor more towards 1. Called unity power factor controllers and things like this. So those, you might hear of those, and the purpose of those things is essentially to ensure that the power factor becomes more like 1, which is what the utilities want. Yeah?
So what would cause a big building to have a low power factor?
Right, so the most common, and we won't go through exactly the mechanisms here, but if you do have what are called inductive loads, so basically loads that have a big inductance to them, the most common of those being motors. Motors are an inductive load that do create a fair amount of, that do essentially draw a fair amount of reactive power, AC motors in particular. We won't get into why that happens, but that is one load that tends to cause some amount of reactive power. So big industrial buildings, for example, that have a lot of motors will oftentimes have very poor power factor and need to actually account for that kind of at their site. I mean, obviously the motors use power as well, but they use real power, of course, too, or they wouldn't be able to do any work with that motor. I guess they could just spin a lot if they weren't doing any work at all, potentially. But actually, that's just probably a good example, because you could think of a motor that would just spin without doing any work, and in some sense that would be drawing reactive power. But big industrial loads do sometimes have significant reactive components. Yeah?
You said there is a regulation for building.
So it varies a lot, and they're not always enforced that much. There are some regulations. I'm actually not familiar with the precise regulations here. I know that some utilities have supposedly regulations about what your power factors can be. Ironically, actually, in homes, these are often quite bad. I do a lot of work monitoring electricity in homes, and because homes are never really monitored for these things, and you might have a motor, say, in your dryer or something like this that spins, you actually can create some pretty big inductive loads in a home, and often power factor in homes are surprisingly bad.
Why don't you put regulation on landslide?
Yeah, you could do that. I guess homes are not seen as a big enough problem from a utility's perspective to really matter. You can smooth a lot of these things out, again, by capacitors, right? So capacitors, just putting a capacitor, one way of doing that essentially is making the power, the power angle come more back to 0 from, say, a power angle that encourages some reactive power. Right, so that would decrease the power angle if you add capacitors. So there are these things you can do, like adding capacitor banks on transmission lines or distribution lines that kind of take that problem away. And because they're sort of on smaller scales, utilities typically don't care that much about homes that do it. They care more about big industrial loads that will have very, very large consumption that still have bad power factor here. Yeah?
So they don't think about the residentials as a huge aggregate?
I mean, you probably could want to, but they, as of yet, have not been as big a problem, or something utilities really thought about that much. Part of this is because I think this is part of the issue, is that as you have a big radial network that provides power at different points, you can do things like have capacitor banks that will actually fix those things and sort of provide reactive power kind of at these different levels. The other thing, which we'll see when we talk more about power flow, is that reactive power is much easier to deal with kind of at the local level rather than at the generator level. So generators can, in some sense, generate reactive power, but it's not the best thing to do because the losses, again, talking very strangely about losses of reactive power, but there you can talk about in some sense loss of reactive power, and those happen it's sort of at much greater rates over transmission lines. So you kind of want to provide support for reactive power locally. That doesn't really answer your question because you might still say, well, okay, that even means we should be more into accounting for reactive power. I think it's becoming more and more a problem, but as of yet, they just didn't want the overhead of doing this. But it is becoming more and more a problem as we have kind of smaller and smaller margins on our generation capacity. these type of things.
So the biggest problem is the loss that reactive power.
I wouldn't say it's the biggest problem. I would just say that it's hasn't been the way utilities will meter. What happened here? Oops, went to sleep. It has not yet been the way that utilities will actually meter power, and so they haven't really been thinking about correcting that at the small residential load level, because you have to, I mean, are you really going to make each home buy a power converter that can make a unity power factor in every single home? It seems a little bit difficult. They would rather just handle that at the aggregate level themselves and provide reactive power support at that level. For a big company, though, it certainly makes sense for them to mandate, or a big industrial plant, it certainly makes sense for them to mandate that you do limit your power factor, or keep it close to 1, rather. Okay, so I think we are getting to the end of time here. About 4 minutes left, but this is the last slide on oh no, sorry, I have one more slide, so perfect. Okay, so real power, so we have 3 different kinds of power, right? We have real power, we have reactive power, we have apparent power. These are all the same units, right? They are all voltage times current, which we know from our units of power are watts. But because people like to distinguish between different things, they actually use different units for each of these. So real power is denoted in units of watts. So real power, whenever you talk about real power, or whenever someone mentions wattage of a device, they're talking about the real power consumption of that device. So if this is a 100-watt light bulb, that is the real power consumption of that light bulb. Light bulbs, at least the filament ones, don't really consume much reactive power. But as we'll see next time, that isn't always true for things like CFLs. When we talk about apparent power, remember the units of watts are volts times amperes. So people decided to use for unit of apparent power volt amperes as the unit of power for apparent power. So if someone talks about volt amperes, which you don't see that much because people don't talk about apparent power all that much, but that means volt amperes is the unit for apparent power. And finally, reactive power, we need one more unit, and they just call it volt amperes reactive, or VARs. So when we talk about VARs, that is reactive power. So you'll oftentimes see sort of power diagrams that show consumption in watts and then consumption in VARs. And that is breaking down consumption by real power and then reactive power. So that, I think, is the last slide. So good timing. We did not get the generators or three-phase power. You do, unfortunately, have a question on three-phase power in your homework, but it's only the last question. So we have 2 days, so presumably people aren't that ambitious that you can't wait to finish the problem set by Thursday. So hopefully it'll be okay if we can wait till Thursday to talk about three-phase power. But we'll see you then.